All right, so I'm going to go ahead and start here. Okay, I'm going to review substitution, and we're going to then introduce the idea of elimination. And before we introduce the idea of elimination forms alkenes. So we'll start discussion of the nature of alkenes. Right. Right, tomorrow's lab is an example of an SN2 reaction. Although in this case, the product will be an alkyl halide rather than the starting material. Okay, so we're going to start off with one butanol, okay, which has this structure. And our goal is to make one bromobutane. Okay, in a nucleophilic substitution reaction, we have the substrate, we have the nucleophile, the leaving group, and the product. Hydroxide is a bad leaving group because it's a strong base. And so what we'll do is we're going to generate HBr by reacting sodium bromide with sulfuric acid. This will produce HBr. Okay, so the oxygen will pick up a proton from HBr. Okay, so this time water will be our leaving group. Okay, so we produce Br minus in that first step. And this will attack from the backside 180 degrees away from that CO bond. And in an SN2, there's a bond formed and a bond broken at the same time. And so our product will be bromobutane. And water, of course.
Dr. Trump, sorry to interrupt. It's kind of hard to hear you over my end. I'm getting most of it, and like the diagrams are easy to follow, but I'm just having trouble hearing you in general.
Okay, let me see if I. Okay, let me try to turn up the speaker volume and see if that'll help. Okay, is that better?
A little bit, yeah.
Okay. Okay, well, I'll try to speak up then. Okay, so I'm going to share my screen. Okay, I'm going to go through some of this fairly rapidly since this is review. All right. So we've been looking at nucleophilic substitution, of which tomorrow's lab is an example. And there are two variations of nucleophilic substitution. There's one called the SN2 and then the SN1. Next week's lab will be an SN1. Okay, we'll also do an elimination reaction in lab. An elimination forms an alkene. Right, in an SN2, nucleophile attacks from the backside. It hits the carbon that's carrying the halogen and knocks it off. In the example that I just gave on the board, the nucleophile was actually a halide ion and it was pushing out water. So in this example, hydroxide forms a bond and iodide. Okay, the transition state has a bond forming and a bond breaking at the same time. It has a trigonal bipyramid shape. Okay, there's just one step in an SN2, there's no intermediate. We can do many things with an SN2. These all follow that same mechanism, it's just a different nucleophile. It is important to recognize relative nucleophilic strengths. Okay, at this end, on the right side, we have the strong nucleophiles. Iodide, even though it's a weak base, is a very good nucleophile because we can distort and polarize the electron cloud. This one with the triple bond and the C minus, that's called an acetylide ion. That's a very strong nucleophile. Okay, these sulfurs with a negative charge are good nucleophiles. Cyanide, oxygen with a negative charge is a good nucleophile. Nitrogen with no charge is a moderate nucleophile. And then at this end, neutral molecules like water and alcohols and carboxylic acids are weak nucleophiles. Fluoride, under most conditions, is also a weak nucleophile. Okay, SN2 depends directly on nucleophilic strength. The stronger the nucleophile, the faster the reaction, because the nucleophile has to come in and actually push out the leaving group. I'll go ahead and reiterate this. Nucleophilicity is actually a kinetic concept, whereas basicity is an equilibrium concept. It's the equilibrium for abstracting a proton. Okay. Okay, be sure you know the difference between protic and aprotic solvents. Protic solvent is one that can accept and donate hydrogen bonds. Generally, a protic solvent, it will have an NH or OH bond. These are aprotic solvents. Acetonitrile, DMF, acetone, and then there's another one down here that's listed called DMSO, dimethyl sulfoxide. SN2 reactions proceed faster in aprotic solvents. Okay, the aprotic solvent will surround cations, but it'll leave anions alone, so they're much freer to attack. Okay, if we go back here, this is in a protic solvent. Okay, notice the anion here, the fluoride is surrounded and bound by these solvent molecules. Okay, so that makes it harder for it to attack the carbon. Crown ethers can allow us to dissolve ionic salts in nonpolar solvents or organic solvents. In this case, the fluoride is very free to attack the carbon and displace the chloride. Leaving group is another important factor. The better the leaving group, the faster the reaction. Okay, these are some examples of leaving groups. Okay, besides halides, leaving groups can be sulfonates, sulfates, phosphates. Okay, tomorrow's lab and also next week's lab, the leaving group is going to be water. Okay, relative rates. The less hindered or less crowded the substrate is, the faster it'll undergo SN2. Okay, methyl's the fastest, followed by primary. Tertiary will not undergo SN2. Okay, the tertiary substrate is too crowded. Secondary can go either way. Okay. Neopentyl is a primary, but it's very crowded in back. So you can see the relative rate compared to 2-bromopropane is very, very slow. SN2 proceeds with inversion of configuration. Complete inversion, so we're starting off with S2-bromobutane, and our product is R, butan-2-ol. In tomorrow's lab, our leaving group is on carbon number 1, which is not a chiral center, so you would not know if inversion took place since we're starting out with a compound that is achiral. Okay, the SN1 is a unimolecular reaction. It's first order, it depends only on the alkyl halide concentration. It goes through a carbocation intermediate, which the SN2 does not. There's 2 steps. Okay, instead of a bond forming and a bond breaking at the same time, halide leaves, or in the case of next week's lab, it'll be water that leaves, and we'll get a carbocation. The nucleophile then comes in and attacks. Okay, this is, in an SN1, this is the slow step. Okay, it's reversible. Even a weak nucleophile can very rapidly attack a carbocation. If the nucleophile is neutral, there's an extra step that involves removal of a proton at the end. There is an intermediate in an SN1. Okay, that's this right here, that's the ions. The first step has a much higher activation energy, so it's a slow rate limiting step. And then the second step occurs very quickly. Okay, substrate reactivity is just completely the opposite from SN2. Tertiary substrate is the fastest, and a primary and methyl will not undergo SN2 at all. I mean, SN1 at all, sorry. And again, secondary can go either way. Okay. Polar protic solvents are best for SN1 because they help separate the ions and slow the rate of the ions coming back together. Racemization occurs because the carbocation is flat. The nucleophile can attack from either side. Okay, so in this reaction, we'll get equal amounts of both enantiomers. Rearrangements are common, okay, because there is a carbocation intermediate. The most common types of rearrangements are the hydride and the methyl shift. Okay, make sure that you do the pushing electrons. That will help you a lot as far as understanding rearrangements and arrow pushing. Okay, here's a summary of the difference between SN1 and SN2. Okay, substrate reactivity is just completely the opposite. For an SN2, you have to have a strong nucleophile. For an SN1, a weak nucleophile is okay. And oftentimes the nucleophile is the solvent, water or ethanol or methanol. SN2 you can do in a protic solvent, but it goes faster than an aprotic solvent. SN1 works better with a polar protic solvent, again, because that keeps the ions separated. SN2 is second order kinetically, first order in each one of the reactants. SN1 is first order. Okay, since the rate determining step does not involve the nucleophile. SN2 involves inversion, SN1 racemization. Okay, since SN2 does not involve a carbocation, there's no rearrangement. But rearrangements can occur in SN1. Okay, let's move on to the next chapter. Chapter 7. Okay, so we'll actually have two chapters on alkenes. This chapter is the structure and synthesis of alkenes. The next chapter after this is the reactions of alkenes. Okay, so we're going to talk about reactions in which the alkene is a product. In the next chapter after this, we'll look at reactions in which the alkene is the starting material and we convert it to something else. Okay, the opening photograph shows a shark, and okay, the way that fits into this chapter is there's this compound down here called squalene, which has a lot of double bonds in it. And squalene comes from shark liver oil. And It is a precursor starting material for a lot of the steroids. Right, so alkenes are hydrocarbons with carbon-carbon double bonds. Alkenes are also called olefins. That's what they call it in the gas industry. That means oil-forming gas. The functional group of alkenes is the carbon-carbon double bond. Okay, that's what gives the group its reactivity. Okay, relatively speaking, alkanes are pretty unreactive. Okay, we saw that we could react alkanes with halogens if we used heat or ultraviolet light. Okay, but they don't react with a lot of other reagents. A double bond, though, is much more reactive. Okay, so this is the structure of ethylene. Okay, the double bond comes from a sigma and a pi bond. The hybridization of the carbons is sp2. Okay, so these orbitals are in a trigonal planar arrangement. And we have a sigma bond here between the carbon and hydrogen. And then this unhybridized p orbital forms a pi bond with this unhybridized p orbital. All right, so in ethylene, all 6 atoms are in the same plane. Okay, so sigma bonds around the double bonded carbon are sp2 hybridized. The angles are approximately 120 degrees, and the molecular geometry is trigonal planar. Unhybridized p orbitals with 1 electron will overlap, and this forms the pi bond. Okay, so here's ethylene versus ethane. Just a comparison of the bond lengths and bond angles. Okay, in ethane, these carbons are tetrahedral, so the bond angles are going to be about 109.5. And notice the bond lengths are greater in ethane than in ethylene. Okay, these bond angles, approximately 120 degrees. Okay, sp2 hybrid orbitals have more s character than sp3 orbitals. What that means is that the electrons will be drawn closer to the nucleus. Okay, so sp2, that means that that orbital has 1/3 s character, an s and 2 p's, and sp3 would have 25% s character. Okay, so a carbon-carbon double bond is stronger and shorter than a single bond.
Just to be clear, you said that in the sp2 hybridization, it means that the electrons will be closer to the atom. Is that what you said?
Yeah, if we back up to this diagram, these electrons will be pulled closer to the carbon, and that results in a shorter bond. Okay, so this is 1.33 angstroms, this is 1.54. Okay, so here's an electrostatic potential map of ethylene, and this will be important in the next chapter because you can see that where the pi bond is, that's very electron rich. And so alkenes are going to attack electron deficient groups. Right, when you have a double bond, cis-trans interconversion is difficult. You actually have to break the pi bond before you can transform into the other isomer. Okay, so you don't have free rotation. Okay, next we're going to talk about something called elements of unsaturation. This is important in terms of qualitative analysis of organic compounds. In November in lab, we're going to spend a couple of labs talking about identification, analysis of organic compounds. And if we have a molecular formula, okay, that gives us some important information. Okay, so propane is a saturated hydrocarbon. The ratio of hydrogen to carbon is 2n plus 2 to n. Okay, every time you have a double bond, you lose 2 hydrogens. So we call that one element of unsaturation, or it's also called index of hydrogen deficiency, or I sometimes call it UU, unsaturation units. Okay, if we form a ring, we lose 2 hydrogens. So that also has one element of unsaturation. So propane is C3H8, propene and cyclopropane are C3H6. Okay, to go from an alkene to an alkyne, we lose 2 more hydrogens. So a triple bond has 2 elements of unsaturation. Okay, so if we have a molecular formula, we can calculate the elements of unsaturation, and that actually provides us with some important information. Okay, this calculation cannot distinguish between unsaturations for multiple bonds and those from rings, but you may have other information that would provide that distinction. Okay, these are examples of nitrogen compounds that have one element of unsaturation. Okay, I think there's actually an easier way to calculate elements of unsaturation than what the slides tell you. Okay, so we have C4H9N. Okay, notice we have an odd number of nitrogens. Okay, that's because nitrogen typically forms 3 bonds. Okay, so what we can do, what I do is I will subtract 1 hydrogen and the nitrogen. So this gives me C4H8. Okay, that's a ratio of 2 to 1. The fully saturated compound would be C4, and then 2n plus 2 would be 10. This is the fully saturated. Okay, so that means we're missing 2 hydrogens. Okay, 2 hydrogens, therefore 1 unsaturation unit or element of unsaturation. Okay, other heteroatoms. Halogens form 1 bond, just like hydrogens do. So we can think of halogens as being like hydrogens. Okay, so for example, say we have C6H4 Cl3 Br. Okay, so what you can do, we can think of halogens as being like hydrogens. So this would be like C6H8. Okay. Okay, I just converted each halogen to a hydrogen. Okay, you follow? Okay. Okay, so the fully saturated, make sure I'm still on screen. Okay, so this is C6H8. It's like C6H8. Okay, the fully saturated would have how many hydrogens?
14.
14, good. Okay, 2n plus 2. Okay, 14 minus 8 is 6. Okay, and these come in pairs, so therefore we would have 3 elements of unsaturation. Okay, so we treat halogens just like hydrogens. Okay. The next bullet point, oxygen does not change the CH ratio. Okay, so if I had oxygen and I had sulfur, we could just completely ignore those. Okay, that's not going to change the CH ratio. So it would still be 3 unsaturation units if this were my formula. Okay, nitrogen is trivalent, so we can subtract a hydrogen and a nitrogen. We would do that for each nitrogen. Phosphorus is right below nitrogen in the periodic table, so if we had a phosphorus, we would do exactly the same thing. Okay, so here we have C4H7Br. Okay, so this would be equivalent to C4H8. And the fully saturated would have how many hydrogens? 10, good. Okay, so we're missing 2 hydrogens, therefore 1 unsaturation unit. Okay, so that unsaturation unit could be a ring or a double bond. Okay, without other information, we wouldn't know. But that's helpful to know. It's also helpful to know if we don't have any unsaturation units. Okay, C6H7N. Okay, so if we subtract 1 hydrogen and the nitrogen, this is like C6H6. Fully saturated would be C6H14. Okay, so we are missing 8 hydrogens, therefore 4 unsaturation units.
Wait, Dr. Trump.
No.
Yeah, I have a question. You mentioned that if there is oxygen and sulfur, we can ignore them. Why is that so?
They don't change the hydrogen to carbon ratio.
Aren't they also bonded directly to the carbon?
Yeah, they are. Okay, so if we take take a simple example of, okay, here is ethane, and here is ethanol, here is ethyl ether, or methyl ether, I guess it is, methyl ether. All right, so this is C2H6. This is C2H6O. This is also C2H6O. And you can see that the presence of the oxygen doesn't add any unsaturation units. It has no effect. Okay, same way with sulfur. Sulfur forms 2 bonds. So we can completely ignore oxygen and sulfur in the formula. All right, next we'll look at IUPAC nomenclature of alkenes. Okay, you can recognize an alkene because it'll end in ENE instead of ANE. We will number the chain so that the double bond has the lowest possible number. In a ring, the double bond is assumed to be between carbons 1 and 2. Okay, so here are some examples. Okay, there are 2 different IUPAC names that are given here. The older systematic name would call this 1-butene. The change came about in about 1998, I'm going to say. There was a newer method, and that is to put the location number right next to the suffix. So instead of 1-butene, it's but1ene. Okay, and then the 1 is because the double bond is between 1 and 2. Okay, so this is pent1ene. And then down here, this is but2ene because the double bond is between 2 and 3. This one is pent2ene. Okay, it would not be pent3ene if we went this way because we want to give the double bond the lower number. And if you say cyclohexene, okay, notice there's no number. It's assumed that the double bond is between 1 and 2. Okay, if I say pentene, okay, we don't know where the double bond is. Okay, so I have to specify pent1ene or pent2ene. Okay, since the double bond is between 1 and 2, we want to give the substituents the lowest possible numbers. And so the structure on the left, we would call that 1-methyl-cyclopentene. Okay, and again, it's assumed that the double bond is between 1 and 2. Okay, for this one, okay, we can't change direction. So if we call this 1, this has to be 2. But to call this 5-methyl-cyclopentene would not give it the lowest number. So we go this way, and so it's 3-methyl-cyclopentene. Yeah.
If we have any other functional group, do we always like number the double one first and then just number the functional groups? Should our priority be the double one?
We're covering functional groups in approximately ascending order of priority. So if it's a halogen or an alkyl substituent like a methyl or ethyl, those are lower priority than an alkene. But then other groups that we have yet to cover, like alcohols and ketones and all those are going to be higher priority. Okay, there's a whole priority listing. And we're going to look at approximately ascending order of priority. Okay, if we have 2 double bonds in the same compound, okay, the prefix for 2, multiplier prefix for 2 is di. So it's a diene, and usually we have to locate both of those double bonds. So in this example, this is buta 1,3-diene. Okay, buta 4 carbons, and then diene 2 double bonds. If there's 3 double bonds, then it's a triene. So this is hepta 1,3,5-triene. Okay, and this is where the double bonds are located. Okay, here's a tetraene, 1,3,5,7 cyclooctatetraene. Okay, here's a couple of examples of alkenes as substituents. This is a methylene substituent. And so the easiest way to name this compound below it is to call that a methylene substituent, the alkene that's external to the ring. So this is 3-methylene cyclohexene, double bonds between 1 and 2, so that puts the methylene on 3. This is a vinyl group when it's a substituent, also called an ethynyl group. Right. Okay, as we've seen, alkenes can exhibit cis-trans isomerism. And we put the word cis or trans right at the beginning, usually in italics if we're printing. So cis-pentuene and trans-pentuene. Okay, if we have 2 groups on a alkene carbon that are the same, then cis-trans isomerism is not possible. So these ones are neither cis nor trans. Okay, if I were to switch these hydrogens, that would not change the compound. If I were to switch these, it wouldn't change. So not all alkenes show cis-trans isomerism. Okay, here are some cyclic compounds. Again, if there's just one double bond, we don't need a number to locate the double bond. Trans cycloalkenes are not stable unless the ring has at least 8 carbons. Okay, so smaller rings, okay, we're going to assume that the double bond is cis. Okay, it actually has to be. Okay, if we have a small ring, okay, to form a small ring, this would be prohibitively strained. Okay, and you can't make a model with this. Okay, so you have to have at least 8 carbons to have a trans double bond. Okay, with larger rings, okay, like with 10, this is cyclodecene, the trans is actually more stable. With an 8-membered ring, okay, it says unless you have at least 8 carbons. Cyclooctene, the cis is more stable than the trans, but with larger rings, the trans is more stable. Alkenes have important roles in biochemistry. Okay, physiologically, what does rhodopsin do? Anyone know? What process is it involved in? Vision. Okay. Okay, this is one of the compounds that's involved in vision. Okay, in the isomerism lab, I introduced you to the idea of E and Z nomenclature. Okay, sometimes cis and trans is ambiguous. Okay, especially if we have 3 or 4 different substituents. And I'll go through this again, how we designate E and Z. Okay, in fact, this was the same molecule that was used as an example in lab. This is E1 bromo, 1 chloropropene. Okay, so we mentally divide both sides of the double bond here like this, and then we establish priorities based on atomic number. Okay, and just like with the R and S, except we only compared 2 priorities instead of 4. Right, so on this side, bromine is atomic number 35, chlorine is 17, so bromine wins. On this side, carbon is higher than hydrogen. The 2 higher priority groups are opposite, so this is E. Okay, and if the 2 higher priority groups were on Z same side, it would be Z. Okay, so if I switch the methyl and the hydrogen, that would be the Z isomer. Okay, you can have E and Z with cyclic stereoisomers as well. Double bonds outside the ring can show stereoisomerism. Okay, so here we have the E and Z isomers of this ketone. Okay, and then I have about a minute remaining, it looks like, so I'll finish up with this slide. Okay, here we have 2 double bonds, and so they both can exhibit E and Z isomerism. So in parentheses, 3Z, 5E. So that means the configuration at 3 is between 3 and 4 is Z, between 5 and 6 is E. 3 bromo, and then we also indicate, seems redundant, but we also indicate the positions of the double bond. So this is 3,5-E. Okay, so I'm going to stop there since I'm out of time, and we'll pick this up again on Friday. Okay, I'll see you tomorrow.